So now what I want to run through real fast is instead of working with these abstract logical expressions, give some actual nice little examples of proofs and use them to illustrate a couple of different proof strategies, a couple of different types of proofs. So a few types of proof. And also just to, get out of our drought of not actually proving anything, but just talking about logic. So the first one I want to talk about is just direct proof. So what this means is we're trying to prove something like, what we want is something like P implies Q. And the way we argue is we start with the premise P. Maybe we have some more premises, or maybe we have some intermediate steps, and then we conclude Q at the end. So you're going, you're starting directly from the start to the finish. Maybe it's not super clear what I mean by that now, but when we get into other types, it'll become clear why this is direct as opposed to something else. So here's an example. So something quite basic, but just to give a taste of, concrete, detailed proof. So if n is odd, then 3n plus 1 is even. So in order to make precise proofs, we need precise definitions. So just to fix ideas, odd means there exists k. Let me not write the symbols, but you can see that there's a quantifier going on there. Odd means n is 2k plus 1 for some integer k. And actually, I think I should write this a little more clearly. So if n is an odd integer, then 3n plus 1 is an even integer. Okay. Quick proof, not too complicated. So by definition, we can write n equals 2k plus 1. For some integer k. Then if we just do some arithmetic, 3n plus 1, substitute that in, is 2k plus 1, which if you work it out is 6k plus 3 plus 1 is 4. And I should say also even means n is equal to 2l for some integer l. And this we can now rewrite as 2 times 3k plus 2. So 3n plus 1 is 2l, where l is equal to this thing. So it's even. Okay. And it's traditional, if you like, to put a little box to denote the end of a proof. Proof complete. look at another one now, which is proof by contrapositive. So in this situation, we want something like P implies Q, and we argue something like not Q with some intermediate steps, and conclude not P. So we are using the fact that P implies Q is equivalent to not Q implies not P. This is why it's called proof by contrapositive, is that we're proving the contrapositive instead of proving the original statement. But of course, this is still valid because they are equivalent. And so this is starting to be what I mean by a direct proof. This is not a direct proof. This is proving it from a different direction, you could say. So let's give an example of this. If n squared is even, then n is even. So we'll prove the contrapositive. And what is that? So remember, the contrapositive is you change the direction and negate both sides. So it should look like n is not even implies n squared is not even. So n is odd implies n squared is odd. And this is going to be easier than the other direction, because this way is going to be basically just some arithmetic. And this way, I think you would have to be a little bit more subtle about divisibility and facts about prime factorization and things like that. We don't have to worry about any of that this way. So by definition, we can write n equals 2k plus 1. And then we can just do some nice arithmetic. N squared is equal to 2k plus 1 squared, which is, if you FOIL it out, 4k squared plus 4k plus 1. And this we can rewrite as 2 times something, 2k squared plus 2k plus 1. So n squared is 2l plus 1, and is therefore odd. That's an example of a proof by contrapositive. Finally, how much do we have left? We have room. Hopefully we can finish this. Proof by contradiction. So this is another sort of indirect strategy. And the way this one looks in outline is we want some proposition to be true. And we argue that starting from the premise not P and some intermediate steps, we arrive at a contradiction. So something that is always false. So the way this works is, let me rewrite this. So let's say we have not P and some intermediate steps, and then a conclusion. So this works because, or I should say this only works if all of our intermediate steps are valid, are true, like proper use of inference and true premises. Because the way we're making this argument, the logic that we're taking advantage of, is that if the conclusion is false, then one of the premises must have been false, and it can only be this one. So we conclude that not P is false, which is to say that P is true, as we wanted. So let's see an example of this. We want to prove that the square root of 2 is irrational. So just to review, a rational number is a fraction of 2 integers. So, which is to say root 2 cannot be written as r over s for any integers r and s. So how do we prove this? We will prove, we will proceed by contradiction. So what we say is, suppose that it is rational. Right, square root of 2 equals r over s in lowest terms. So we're supposing root 2 is rational. Then we can write it this way. And what do we mean by lowest terms? We mean that we can't reduce it any further. We mean that r and s have no common factors. So in particular, r and s are not both even, right? And then we can say the following. So consider r squared divided by s squared. This is r over s squared. So this is the square root of 2 squared, just 2. So we can rewrite this as r squared equals 2s squared, and r squared is even. And if you remember the thing we proved just before this, we can conclude that r is even. Okay, so a lot of just, okay. So r squared is twice s squared, so it's an even number, so r is an even number. But now, we can do the same thing in reverse. Since r is even, we can write r equals 2k for some integer k. And then r squared over s squared equals 4k squared over s squared, and is still, as before, equal to 2. Oh, I think we'll just have room. My goodness. So we can rewrite this as 4k squared equals 2s squared. And we can reduce that to 2k squared equals s squared. So s is even, or sorry, s squared we can conclude is even. So s is even. And now you will see that we assumed that r and s are not both even, and we concluded that r is even and s is even. So this is a contradiction. We have proven R and S, or not R and S, and also R and also S, right? This is a contradiction. And that completes the proof, because that was the whole idea. We will start with the assumption that our conclusion was false, and as long as all of the rest of our steps were a valid mathematical argument, then arriving at our contradiction means that we have proven the thing that we wanted to prove. So these are a couple of examples of proofs and a couple of examples of proof structures. Don't worry if it doesn't all make sense already. I went through all of that kind of fast. The point was more just to, first of all, finally give some nice concrete examples of proofs. This one at the end in particular, the fact that root 2 is irrational, that's an interesting fact. You know, that's like something that a mathematician might actually care about. So, you know, we're starting to get into the things that are like really, you know, real mathematics. But also just to give you some outlines for how proofs might go and some starts with looking at these kinds of things. Not to worry, we'll be talking a lot more about this in the next few days. So if you don't understand it yet, there will be plenty more time for that.